This is lecture 24 on urban transportation planning. We will continue our discussion on trip distribution analysis in this lecture. You may recall we discussed about the structure of doubly constrained gravity model in the previous class, and then we understood the method of calibration of doubly constrained gravity model with the aid of a numerical example. Calibration mainly involves determination of the parameter related to the friction factor Fij, right, and the calibration process involves taking into account the trip production adjustment factor as well as trip attraction adjustment factor. You may recall we assumed a trial value for the parameter alpha, also a value of unity for the trip production adjustment factor Yj, isn't it. Then started the iterative process until both Xi and Yj balanced. Then the balanced values of Xi and Yj along with the assumed value of alpha was substituted in the parent equation or the parent doubly constrained gravity model to get values of Tij. Thereby we will be able to get a matrix giving the result of your trip distribution using doubly constrained gravity model. Then this matrix should be compared with the actual observed distribution matrix cell by cell, and the effectiveness of matching of your model generated matrix with the field observed matrix can be tested using statistics like normalized phi, normalized mapser, as well as coefficient of determination. That is what we discussed in the previous class. To check whether we have captured the essence of the previous lecture, let us just pose few questions to us and let us try to answer the questions. The first question is this: what is the main difference between the singly constrained and doubly constrained gravity models? You should not simply answer that singly constrained model is having one constraint, doubly constrained model has two constraints. It should be more detailed and technical answer. Any volunteers? Only one difference, main difference between singly constrained and doubly constrained gravity model. The answer is this: the constraint related to trip production, zonal trip production, is built into the model itself in the case of singly constrained gravity model. In the case of doubly constrained gravity model, we take both the constraints related to trip production as well as trip attraction in the model structure itself, so that the constraints are given as input to the model and get the constrained model formulation before we actually start distributing the trips using the gravity model, right. Constraints related to production as well as attraction go into the model structure in the case of doubly constrained gravity model, whereas in the case of singly constrained gravity model the constraint related to only production is taken into account. Clear? So that is how we need to understand the difference between these two models. One other question which is very relevant is this: why the data needs to be segmented for trip distribution analysis? I hope all of you understand what we really mean by data segmentation. What is data segmentation? Physical meaning of the word segmentation, I think all of you should be able to appreciate. Segmenting is separating into parts, isn't it? why should we segment the data for trip distribution analysis? Please remember, when we collect trip distribution data for base year condition, we will have information about distribution of trips from one zone to all other zones, irrespective of the distance involved, irrespective of the mode used, right, irrespective of the purpose for which the trips are made. All this information are collected together, right. So it is a conglomerate of all these types of trips distributed from one zone to all other zones. But we want to segregate or segment the data for the purpose of distribution of trips. Why? Because trip distribution pattern depends on certain important factors. Trip distribution pattern is influenced by the mode used for travel. As I indicated to you repeatedly, if the mode is just foot, trip distribution pattern is going to influence only the adjoining zones from the zone under consideration, isn't it? If it is bicycle, it may extend over a slightly larger region. Motorized modes may extend over the entire urban area irrespective of the distance. So that is how mode used for trip influences distribution of trips. Obviously, we need to segment data based on mode used for transportation, isn't it, before you distribute the trips. And if you feel that in a particular urban area the trip purpose also influences distribution of trips, which may be true in most cases. Take for example shopping trips. Shopping trips mostly may have influence over the adjoining zones. Very rarely people go over long distance for shopping, unless it is a very important retail purchase. Normally we do shopping in the adjoining areas. And the educational trips are relatively shorter compared to work trips. If you look at the average length of educational trips and work trips in any urban area, you will find that the average length of work trips is slightly more than the average length of educational trips, because we put mostly children in the school around the residential areas, unless the parents are very particular to put their wards in specified schools of their liking, which might be in far up places, which may not constitute a major percentage proportion, right. So there is a reason to segregate data based on trip purpose also, because distribution pattern might depend on the purpose of trip too, isn't it. So that is the question here, why the data needs to be segmented for trip distribution analysis, because trip distribution is influenced by factors like trip purpose, mode of travel and so on. Therefore, there is a need for segmenting data before we do trip distribution analysis. Clear? As we did in the case of mode choice analysis, we did not put everything together and did mode choice analysis, we segmented data, isn't it. On the same lines, there is a need for data segmentation for distribution also. Third and the last question is this: how the correctness of the calibration is checked in the case of number 1, Bpr method of calibration of singly constrained gravity model. How do we check the correctness of calibration? In the model calibration process, you may recall, we just express Fij as a function of Tij, right. In Bpr method also we express the friction factor as a function of mostly travel time and very rarely travel distance, okay. And how do we check the correctness of calibration? what do we do in Bpr method of calibration? At the end of the calibration process, what do we do? You may recall we are using discontinuous function, right, to get the different functional forms for the friction factor. It is not a single function, and discontinuity is based on the segmented travel time. Put all the trips involving times of 0 to 5 minutes as one group, right, and then try to fit a functional form for that particular data set. Then put all the trips involving travel times between 5 and 10 minutes and identify a functional form and do calibration, right. So, after completing the entire data set, what we do is we find out, based on the results of the calibration, what proportion of trips fall under each segment, what percentage proportion of trips fall under each segment, 0 to 5 minutes, 5 to 10 minutes, 10 to 15 minutes and so on. And after doing the calculation, we can draw the trip length frequency distribution curve, right, and the same thing can be done using the actual observed data. On the same set of axes, you draw both the trip length frequency distribution curves, isn't it, and then check visually for matching of the two curves. If they are not matching, then there is a need for correction for the friction factor, which was derived based on the functional form assumed for Tij. Do correction for the Fij value and repeat the process until there is a reasonable match between the two trip length frequency distribution curves developed based on the gravity model and based on the actual observed data. That is how we check for the correctness of calibration by Bpr procedure. Clear? And how do we do the same thing in the case of doubly constrained gravity model? What do you get? What form of result you get when you use doubly constrained gravity model for trip distribution? Would you be getting trip length frequency distribution curve or something else? We will be getting a matrix giving trip interchange information between zonal pairs at the end of, right, distribution of trips using doubly constrained gravity model. You will simply get a matrix, and you will have a matrix based on field observed data for base year condition. So, there are two matrices available. It is a question of comparing the two matrices by comparing the values of the corresponding cells, 1 1 with 1 1, 1 2 with 1 2 and so on, right. This comparison can be done using a set of statistics as we discussed earlier, and basically we will be comparing two matrices and check for the closeness of the two matrices using the standard statistical measures like normalized phi, normalized Mapser and coefficient of determination, right, until a satisfactory result is obtained. That is how the correctness of calibration is checked in the case of doubly constrained gravity model, right. So, please take an overview and have a comparison of the two methods. That will help you to understand the basic principles involved in the exercise much better. Clear? You may recall at the end of the previous class we took up a case study to understand the application of gravity model for trip distribution to a real life situation. The city considered was the city of Tiruchirappalli, and I gave you some information about the city. The city is located in Tamil Nadu state, India, and the public transport mode available is only bus and private transport modes: car, motorized two-wheeler, bicycle and foot. Intermediate public transport modes: taxi, auto rickshaw and cycle rickshaw. And then trip purposes, as we have seen earlier, are only 3: work, education and others. And total number of traffic zones in the study area 85, out of which 49 zones were in the urban area. And it will be appropriate to show you the picture of the study area of the city, so that you can have a feel of the urban area and total planning area and so on. So this is how the study area looks. The green colored portion is the urban area. The boundary of the green colored portion is the municipal boundary, municipal administrative boundary, and the outer boundary indicated here is the planning area boundary. This implies that we collect information about socio-economic characteristics and transport system characteristics in the whole of the area bounded by the outer line. Clear? Look at the proportion of area of the urban pocket and the whole of the planning area. The area surrounding the urban pocket is huge. So we should not have an impression that urban transportation system planning means working within the municipal boundary. It is not so, right? Then you may wonder, why should we go so far, and how do we fix the boundary, where to stop and so on, right? And how do you fix the boundary? You must have some reconnaissance survey and identify the places around the urban area where from people commute to the city center on a regular basis. That means such people are contributing to the city's traffic, congesting city's roads, right? So their movement is unstoppable because they commute on a regular basis. So unless you include that area also in your planning study, you will not be getting the realistic picture of the traffic on city roads, right? So we have to identify the adjoining areas which contribute to the city's traffic on a regular basis, include all those areas into your planning process and then fix the boundary. That is the basic principle. Clear? And the surrounding areas may not be truly urban areas, they will be just panchayats, town panchayats, major panchayat, minor panchayat and so on, right? But still you may have to include because they all contribute to the city's traffic. Clear? So that is how you must be able to perceive the planning area boundary in the case of urban transportation system planning. Another interesting aspect is that the total number of traffic zones were 85, out of which 49 zones were within the urban area. Very small area, more number of relatively large number of zones, and for rest of the area which is very large, we have fixed only small number of zones. Why? Still we believe that we may get fairly accurate result in spite of this kind of coarser division of the area surrounding the municipal boundary. Why should we have more zones in a smaller urban area compared to the number of zones in the peripheral areas or outside the urban boundary? Obviously, the intensity of socio-economic activities is very high in the urban area. Even if you say take a small area, the number of people living will be large compared to the peripheral areas. If you take one panchayat, there will be a cluster of houses as bunch in one location, rest of the area will be just agricultural land, right, whereas here it is heavily built up and activities are concentrated. So obviously we need to divide the area into very small land use parcels, so that within that area the land use is more or less homogeneous, and still the number of people involved are more relatively large in number compared to the concentration of population outside the city boundary. That is the logic of having more number of traffic zones for the smaller size of the municipal area and then less number of traffic zones. And another important aspect is, when you divide the traffic zones, we are fixing one centroid and consider that as a trip origin and destination, isn't it? When you consider very large areas outside the municipal boundary, and when you fix only one point as I indicated to you earlier, then we will be doing approximation, lot of approximation representing all the trips spread over a vast area to be emanating from a single point, isn't it? But in practice what we do is, we divide of course the peripheral areas into larger land use parcels, but the spread of the population, spread of socio-economic activities will not be uniform throughout, it will be over smaller cluster, right, one or two streets in a village, right. Fix that as your zone centroid. It need not necessarily be the geometric centroid of the area considered, it is the centroid of intensity of activity in that particular land use parcel. Then you can accurately represent really the trip origin as well as trip destination. That is how we manage fixing the zone centroid in the less populated peripheral areas, clear. So that is how we can justify having more number of zones within the urban area and less number of zones outside. And you can see two major rivers crisscrossing the city in addition to a small water course on the southern part. That is why I said this city is basically an agricultural city, and city's economy is agro based, clear, except for one major industry, Bharat Heavy Electricals, located somewhere here. The rest of the area is with lot of green fields, mainly paddy, okay, and so on. With this understanding of the study area, let us go further to see how trip distribution analysis was done for this particular case. What I will be discussing is not the distribution which was done for the practical purpose of planning. It is a demonstration of trip distribution. It is a kind of demonstration project involving the zones only in the urban area. So our distribution discussion is concerned with the 49 zones, right, within the urban area. It is possible to mark off some areas, still analyze the distribution of trips. Only thing is, you must leave off the trips which go beyond your urban boundary. Consider all the trips which are getting distributed within the urban area and then do the trip distribution analysis, it is possible. This is the data of trip production and attraction in the base year within the municipal boundary. You can see some interesting numbers. If you look at zone 3, there is no trip production for work, there is no home or household where from people go for work from this particular zone. Also there is no trip production for education, and there are a negligible number of trips produced for other purposes, right. Basically this zone is a trip attraction zone, we can say purely a trip attraction zone, clear. and if you look at the numbers of trips produced and attracted, you can see a vast variation. Of course least value is 0 as you have seen, and the numbers touch what is the maximum that you see in this table, about 16,431 trip attractions for zone 7. Yeah, there is one 21,000 plus also, right, 0 to 21,000, vast variation. That is how we come across numbers in practice. And the same data for other zones 10 to 18 and you can see the numbers have reached values of 25,796 appears to be the maximum of trip production, and attraction also has touched nearly 24,121 appears to be the maximum of the trip attraction values. Here again you can see zone 14 there is no trip production, it is only an attraction zone. 15 also there is no trip production, only trip attraction, that too the attraction values are much less. What could be the type of urban area with this kind of characteristics? When you look at the data you must have a feel of the field condition, then only you will be able to appreciate your results of analysis. Very less number of trip attractions, mostly some could be some workplaces. As I said, it is agro based economy, maybe some agricultural fields which attract trips, okay, people go to field for work, right. There may not be large number of trip attractions to fields, a limited number. So that is why you must have a feel of the land use of the area when you look at these numbers. And when you look at trip attraction numbers of say 24,121, obviously you must think of a very intense commercial area or industrial area and so on, right. And then zone 19 to 24, similar variations, and you can see mainly the large numbers are related to work and education, obviously because of the high percentage of trips made for these two purposes. And then zones 25 to 35. So we have come across quite a few zones with no trip production, only purely trip attraction zones, and the values vary from 0 to 25,000 plus. Okay, this data has to be used for distribution of trips. How are we going to use this data? We have already segmented the data based on trip purpose, work, education, others. So we can take data pertaining to work trips separately and distribute the trips, take the data pertaining to educational trips separately, distribute, and then other trips. That is one way. Other possibility is identify the modes used and distribute the trips based on mode used for travel. Since it is a demonstration project, we wanted to show the result of both the gravity models, both the types of gravity models, doubly constrained as well as singly constrained. Singly constrained gravity model of only one type was used, and here type 1 formulation shown as model 1A is a doubly constrained gravity model, right, and the Fij formulation given here is Dij raised to power alpha, okay, expressed as a function of travel time or travel distance. And interestingly, in this particular case travel distance was taken, or friction factor was expressed as a function of travel distance. The reason is this: this distribution process pertains to only city area, where the road network was found to be more or less uniform. And another reason is that the travel time information obtained was found to be not that accurate. There were some gray spots which we were not that confident of making use of travel time information. As an alternative, we just looked for travel distance as an alternative and found that nothing wrong in using travel distance as far as this part is concerned, because a road network is more or less uniform. The level of congestion, traffic composition, everything was almost same because it is confined to urban area. So as a special case, travel distance was used. It is not common, very rarely people use travel distance. This is one of the cases where travel distance has been used to explain travel deterrence, Fij. And this is model 1A, and of course as you know, xi is given as 1 by sigma j 1 to n yj aj dij raised to power alpha, and yj as we know 1 by sigma I is equal to 1 to n xi pi dij raised to power alpha. And the explanation for all the notations used are known to you. Tij is nothing but number of trips produced in zone I and attracted to zone j when we write Tij, we are talking about base year Tij or horizon year Tij. Base year Tij if we are calibrating the model. For the purpose of calibration, we will substitute base year data as Tij. Once you complete your calculation of the parameter value, or once you complete your calibration process, then use the model, then your Tij is your horizon year Tij that you will be estimating, is not it? Even the notation is same, we need to be careful what we really mean by Tij. And Pi total to production at zone I, okay. For calibration it is the base year value. Aj total trip attraction at zone j, and xi trip production balancing factor, yj trip attraction balancing factor, and dij distance between zones I and j. I said distance, not time, in kilometers, and alpha parameter to be estimated. This was model 1A, and we tried other formulations also for Fij. Model 1B had a different formulation for Fij. It was e power beta dij, and model 1C had two parameter formulation, e power beta dij into dij raised to power -1. The other parameter value was given directly. We did not estimate both the parameters simultaneously, one parameter value was assumed as -1. Okay. So we had three formulations in the doubly constrained gravity model, and then the deterrence factor is an exponential function in model 1B as we have seen, and a combination of exponential and polynomial functions in model 1C, is not it? The two models 1B and 1C are also subject to the constraints in 2 and 3, as we have seen, constraints related to xi and yj, constraints related to production and attraction, that is the meaning. Okay. Then type 2 formulation is this. What is this formulation? It is a very simple singly constrained gravity model. Fij has been written as dij raised to power alpha, otherwise it is a singly constrained gravity model. The functional form for the friction factor has been directly taken as a simple polynomial function as dij raised to power alpha, and the constraint which is taken care of in the model is sigma j is equal to 1 to n Tij equal to Pi is inbuilt into the model, which is automatically satisfied, and other constraint has to be satisfied during distribution process. I is equal to 1 to n Tij to be equal to Aj, isn't it. So totally we have considered 3 plus 1 4 model formulations, 3 formulation under doubly constrained category and 1 under singly constrained category, and the functional forms for Fij has been fixed for all the 4 cases. And how do we calibrate using doubly constrained gravity model? The same procedure. We assume a value for alpha, we assume initial value of Yj, not Yj, Aj, isn't it? Yes, Yj related to the trip attraction factor, adjustment factor, right. Then go about doing the iterative process and finally put these values into the doubly constrained gravity model. The same exercise was done for trial values of alpha. Initially one value of alpha can be assumed and you can complete the iterative process, then assume another value of alpha and so on, and then check which value of alpha gives you better result. Of course this is known to us, friction factor Fij having been taken as Dij power raised to power alpha, and zone to zone adjustment factor Kij in this case is taken as unity, otherwise we will not get this formation. I am giving you directly the result of doubly constrained gravity model. I have shown you the data set, we have used the same data set, the formulations are shown to you, right, and this pertains to variation of normalized mean absolute error over a range of value of alpha for model 1a, right. I hope all of you remember model 1a formulation, it is a doubly constrained gravity model, right, Dij power alpha, it is simple polynomial function, right. So how many trial values of alpha has been tried? 7 trial values of alpha, 7 values have been tried. 1, 2, 3, 4, 5, 6, 7 values. We have tried with 7 values of alpha. And how do we choose the value of alpha finally? Our objective is to choose the right value for alpha, which is the parameter. Look at y axis, normalized mean absolute error. We would like the error to be minimum, or obviously we must look for the alpha value with least error, isn't it? And if you do so, we find this is the lowest point in the curve, gives you the least error, and the corresponding value of alpha is minus 1.75. Clear? So this is how we calibrated model 1a, which is under doubly constrained formulation. Once you know the value of alpha, then you can write the calibrated form of the gravity model like this. This is the calibrated gravity model, very simple. The calibrated model for the work trip based on the value of normalized Mapser can be written as Tij. W I am writing purposely because this calibration was done using data pertaining to work trip. Okay. Pi, Xi, Yj, Aj, Dij raised to power minus 1.75. Now this model is ready for application for horizon air condition, right. What do you get for horizon air condition? How will you apply this model for horizon air condition? What are the values that will be known for you, known under horizon air condition? Obviously you will not know Tij, that is what you want, isn't it. So to get horizon air value of Tij, you should know the values of Pi and Aj corresponding to the horizon air socio-economic condition, right. Unless you predict the values of Pi and Aj, you will not be able to distribute the trips under horizon air conditions, clear. Now the other model using Bpr method, singly constrained gravity model. I am not showing the other formulation, just as an example I have shown you one case, model 1A. Now just I am passing on to model 2 or type 2 formulation, okay, where we just discussed about singly constrained gravity model. The method adopted was Bpr method of calibration, right. And you can see the distance segments used. If you are making a continuous, this do not worry about this curve, this is just to show you the difference between a discontinuous function and a continuous function, okay. What was actually done was assumption of a discontinuous function, and for each segment a separate function was assumed, clear. And as an example I will show you the result of matching of the trip length frequency distribution curves for one case, because this is functional form of friction factor in model 2 for work trips again. This is how the accuracy of calibration by Bpr method was checked for this particular case, trip length frequency distribution for travel by public transport mode. It is based on mode used for travel, okay, right. And you can see some numbers along x axis, 0, 2.00, 4.00, 6.00, 8.00, and then percentage of trips 0, 10, 20, 30, 40 and so on. What does it mean? Let us just look at this point. When I produce a point vertically corresponding to trip length of 2 kilometers, it just intersects the curve somewhere here, right. It is not touching any point. And when I produce another point corresponding to distance of 4 kilometer, it is just again going and touching the curve midway between 2 points. Now based on this information, can you tell me what is the distance segment that has been considered for drawing this trip length frequency distribution curves? Distance segment or length of one segment in kilometers. 2 kilometers, but you have no more number of points here. Since I have indicated 2 and 4 with the red line, you are just telling 2 kilometers or what? Why so many points? How did we get these points? This is percentage of trips out of the total, right. How many points you have from 0 to 2? 1, 2, 3, 4, and if you consider this as a point, then 5, or how many segments you have? 1, 2, 3, 4 segments, right. So this point pertains to trip length of what distance? Suppose I say that this point pertains to trip length of 0 to 0.5 kilometer, 0 to 0.5 kilometer, 0.5 kilometer is somewhere here, let us say 0 to 0.5, then 0.5 to 1 kilometer up to this point, midway between that, then 1 to 1.5 this point, 1.5 to 2 represented by this point, clear. So we segment the distance and then fix the midpoints as representative points to indicate the percentage proportion of trips pertaining to each segment of the trip length. That is how we draw the trip length frequency distribution curves, okay. And it was done for observed case as well as model calibrated or model simulated values. You can find almost perfect matching except for a minor deviation in this stretch, and this was finally accepted as a final value. Subsequent iterations led to more separated curves. So then this was identified as the point of convergence, and this was found to be the correct calibration result, okay. Let us look at the statistical performance of the models that we listed earlier. You may recall we had data pertaining to work trips, educational trips and other trips. We decided to have these formulations, model 1A, 1B and 1C as doubly constrained model. In addition, we wanted to have singly constrained model to be calibrated by Bpr method. That type 2 is not listed here, the results pertain to type 1, all doubly constrained model, okay. And you can see the value of the parameter here. Suppose in the first case it is alpha, second case and third case it is beta, e power beta something we had, you may recollect the model, right. Or if you want to have a look at the 3 models, these are the 3 models we are talking about. 1A, the parameter is alpha, 1B, the parameter is beta, and 1C also, since we assumed value of unity here, again it is a value of beta, right. So that is what we have listed here. And we should have a feel of the logical aspects related to the results that we have got. For example, for work trips in the case of model 1A, we have minus 1.75 as a parameter value. For educational trips we have minus 3.00, for other trips minus 1.85. The value of alpha represents what? Travel, the extent of travel deterrence, Dij raised to power some negative quantity, is not it, or the numerator Dij normally should come in the denominator, is not it, because it is raised to some negative value, right. And when the negative value is higher, what is the meaning? Travel deterrence is more, obviously, is not it. So you will be writing Dij power minus 1.5, or you can say the numerator divided by Dij raised to power 1.5, 1.75, is not it. So these numbers indicate increased deterrence, or in other words you should say that deterrence for travel for work is relatively less compared to deterrence for travel for education, is it right? People have more travel resistance when they make educational trips compared to the travel resistance realized by people for making trips for work. Is it true? What is the result of increased travel deterrence for educational trips? Decreased travel distance, obviously. Practically, if we look at, you have some choice of educational place in the form of schools and colleges with respect to a residential area. If you look at the possibility of making educational trips, there will be a number of schools around a major residential locality, right. There will be number of colleges, so people can choose a school or college depending upon the distance of travel, and you cannot choose a workplace, right. So your workplace is fixed, so obviously irrespective of the distance implication you may have to travel. Choice is less in the case of, almost nil in the case of travel for work. So when you fix your destination, okay, obviously when there is a choice you try to minimize the travel distance, right. So that is how deterrence for travel for education is shown here as higher than the deterrence for work trips. Are you able to appreciate this point, or unless you have a feel of that, then there is no point in looking at this table and these numbers. And of course difference between these parameter values are because of the variation in the functional form, that is how 1.75 minus 1.25 minus 0.5 you are getting, but if you compare the corresponding values the same will be reflected. 1b and 1b, it is minus 1.25, it is minus 2.5, again increased deterrence for educational trips, whereas for other trips which is a mix of trips made for shopping, social recreation and so on, the values are different. We will not be able to explain very clearly these numbers, whereas it is possible to compare these two values. And look at the statistics. The values of normalized MAPSR and normalized phi are all less than 1, and R square values, as you could see, ranges between 0.94 and 0.75. You know what is meant by these R square values. We have discussed enough about the implication of R square value. Normally statisticians say that if the value of normalized phi is less than 0.6, 0.65, we can say that the error is acceptable. There is error, but it is within acceptable limit. The same range is given for normalized mean absolute error also. You may question why not fix it as 0.5 or 0.8, it is up to us, it depends on the accuracy that we insist on a particular case. So you must take a overview, as I was mentioning earlier. If your basic issue that you are analyzing is complex and data is broad based, then you will not be able to get very accurate result. In another case, if it is quite compact, if the data is homogeneous, you can anticipate higher level of accuracy. Depending upon the expectation, you can fix any guiding value as an acceptable value of phi or normalized MAPSR. Clear? Let us look back and see what we discussed so far. We mainly discussed about the application of trip distribution models for distribution of trips in Tiruchirappalli city, and we had a feel of the trip production, trip attraction data for the purposes of work, education as well as other purposes in the city of Tiruchirappalli. And then we considered 3 formulations of doubly constrained gravity model and 1 formulation of singly constrained gravity model, and tried to understand the application and the corresponding results of these models for this particular case In the process we also found as to how to go about fixing the right value of the parameter in respect of one model, namely alpha, based on the normalized Mapser value and the guiding value of alpha, right. Finally, we have seen the logical correctness of the parameter estimates. When you put all the parameter estimates together, we are able to appreciate the logical correctness of the parameter values based on the trip purpose, right. We will stop here and continue the rest of it in the next class.